Oh, hello, awesome physics students. Today we want to talk about energy and work in rotation. And so there's two ways we can approach this. The first way is to use our analogies. That is the things that we've built up, the analogies that we built up over the year. For example, rotational velocity, omega, is analogous to linear velocity, v, in meters per second. And we can build those analogies together and build on what we've already learned. So for example, kinetic energy is 1/2 mv squared. We can build an analogous rotational velocity equation using the analogs of mass, that's moment of inertia, and rotational velocity omega. And those formulas that we built actually are correct and they make sense. So that's my preference. There's another second approach, and that is to look at the equations for the basic definitions for kinetic energy and work, and then manipulate those equations with a particular example to come out with a rotational version of that equation. That's another good approach. I'm not going to do that totally rigorously and you know, not like you would find in a very rigorous and careful dynamics textbook. But I think those can be also motivating too. I think for you guys, I think it's best to lean on the analogies. Okay, so let's go ahead and get started. Okay, so one way to do this is to build on our analogies that we've already known. So on the column here, we have our linear version of things. So time, mass, position, velocity. That's the regular things that we're probably pretty comfortable with from the beginning of the course. And then here we're going to fill in our rotational analogs of those. So the rotational analog of time is still just time, and that's going to be in seconds, of course. The rotational analog of mass, however, is moment of inertia. That we use I, and that is, let me just put I like that, and that is going to be in kilogram meters squared. Oops. All right. So mass measures the amount of inertia, or resistance to change in motion. Moment of inertia, or rotational inertia, same thing, measures the resistance to changes in rotation. Position, the analog for that is the angle, and for that we'll use theta. So let me insert equation. Okay, and that will be the angle analog is theta, and we usually measure that in radians. Okay. For the velocity, we use the analog of that is angular velocity. And for that one, we use the symbol omega. So, and that's going to be in radians per second. Okay. For angular acceleration, or for acceleration, the analog, rotational analog of that is angular acceleration. And we use, for that, we use alpha. So let's go ahead and type that in. And that's, of course, in radians per second squared. Okay. For force, the analog of that, force is the motivation to cause acceleration. So force is what causes acceleration. That's what how we think of it. In this case, torque is the rotational version of that. And for that, we use a Greek letter tau. And that's going to be in Newton meters. Okay. And remember that the formula for torque is that tau is equal to RF sine theta, where theta is the angle between the vector R and F. Okay, there's a rotational version of Newton's second law. And that looks like this. So let me just put it in the equation here. This is the sum of the torques about a certain point equals, well, we're using the sum of the torques because that's the rotational analog of force over here. So here we're summing the forces and saying that equals ma. Here we're going to sum the torques, that's a rotational version of force, and set that equal to what represents inertia, and that what it represents inertia is I, the moment of inertia, and then what represents linear acceleration, that's going to be angular acceleration. Okay, so that works for the rotational second law. What about kinetic energy? Well, the rotational version of that is still kinetic energy. And that looks like 1/2, well, let's do this in equation language. So that's going to look like 1/2 the rotational version of, so here we have mass times velocity squared. The rotational version of mass is moment of inertia, and the rotational version of velocity is going to be angular velocity. So that's 1/2 I omega squared, okay? And the unit for this in regular units is joules. In here, we're going to use, it's the same unit. It's still joules, okay? Let me fill this in, it's joules. All right. Okay, let's move on to the rotational version of work. The rotational version of work is still work. So that's not going to be different, but here we're using an integral, so let's insert an integral. And here we're integrating the force times some distance here, okay? And we're using an integral because the force may not be constant, and this is sort of from the definition. But really, we're taking the part of the force that's parallel to the multiplying it by the parts of the force and the distance that are, or displacement that are parallel, and we're adding them up. So adding them up is the integral. Here we're going to do the same thing, and it's integral. The rotational version of force is torque. So that's tau. And the rotational version of, this is a displacement, the rotational version of displacement is the angle. That's going to be d theta. Okay, so that's, and the units for this were joules in regular units. In rotational units, it's still going to be joules. Okay, then what is the rotational version of the work energy theorem? Well, it's still the work energy theorem. Can't spell that. And that states that the net work done is equal to the change in kinetic energy. The rotational version of that is still the same. The net work done is equal to the change in kinetic energy. But keep in mind up here, we may have both translational kinetic energy, 1/2 mv squared, and we may have rotational kinetic energy, 1/2 I omega squared. So in here, in this term, we may have to consider both kinds of kinetic energy. Similarly, with work, we may have to consider both linear work and rotational work, okay? But since the units of these four entities all line up, we can mix them in the same equation, and that's just fine, okay? So that's how we build these equations from the analogies. Let's look at how you might derive some of these things. And I've derived some of these other things already. We've already talked about those. So let's concentrate on the last little bit here of the kinetic energy work and work energy theorem. And we can sort of connect those dots with some simple examples. Okay, so let's start in with the equation. How would you derive this from equations? We built this up from analogs before, now let's do it with the derivation. And this isn't a rigorous derivation. This is just a derivation that gives you an example of a rotating wheel, for example, and then creates the equation from that for that particular example, and sort of motivates it and highly suggests that this applies in many other situations. So this isn't a general derivation, it's just a specific one. But it's still a very useful one, and because we're making it specific, we can make it more clear. Okay, so imagine you have a rotating wheel, and we want to think about the rotational kinetic energy. Well, we know that kinetic energy is 1/2 mv squared, but because of this, the velocity of each of these points is different along here. It gets bigger as you go out to different larger radii of the wheel. We have to break this up into little tiny chunks and add up the chunks of each of those the kinetic energy of each of those chunks. So really the kinetic energy here is going to be, the total kinetic energy for this whole wheel is going to be the kinetic energy of each of those chunks. So I'm going to say this is the ith chunk. Maybe this is the, we're going to break it up in a bunch of chunks, and I just want to put a sort of a general expression for each of the chunks' kinetic energies. So that's going to be the mass of the ith chunk times the velocity of the ith chunk squared. And because I'm breaking this up into little tiny pieces, I mean, there's just little pieces everywhere. And each of these pieces has some velocity and some mass. I mean, some of these chunks might have a big mass. And, so we have to, we're sort of accounting for that here. Okay. We have to add up the total kinetic energy will just be the kinetic energy of each of those masses, and we just add them up. Okay, so the sigma just is a reminder that we need to add all of those up. Now, let's look at the situation for the ith chunk here. It's going to have a distance from the origin, from the rotation axis. So the axis is right here at the center. And if I work with that expression, I'm going to add up the mass for that. But I want to write the velocity. Remember, the velocity of the ith chunk is just the radius for the ith chunk times, that is its distance from the axis, times the angular velocity of that ith chunk around. Okay, so I'm gonna take that and substitute that in here. So it's going to be r sub I omega sub I squared. Okay, and this is just, remember, this is just coming from this this equation, and we take a time derivative of it, and that gives us v equals r omega, right? So I'm just using that on this ith piece here. Okay, so far nothing crazy. I need to sum this up. Now I'm going to repackage this. So this is the 1/2 here is just a constant. So let me move that out front. I'm going to move that over here. And so this becomes the sum of all the m sub i's. Now I'm going to distribute this squared into each of these terms here. And so this becomes r sub I squared, omega sub I squared, okay? Now it's looking a lot more like something that we can apply our definitions of our rotational entities to. So the 1/2 is out front, and that's in every term. So this term looks like kind of like a moment of inertia, right? We're summing all the m sub I, r sub I squared. The problem is it's multiplied by individual omega sub i's. So this is going to have some omega. This is going to have some omega. And the way this is written, that suggests all of those omegas are different. But that's not true. All of the omegas are the same, right? It's the same omega. That was one of the main advantages of using omega, is because when you have a rotating object, the velocities are all different, but the omegas are all the same. So because these are all the same, this becomes 1/2 the sum of all the m sub i's, r sub i's squared, and then this is just omega. And because this is the omega is the same for all, I can take this out front, and this can become, and this is again the kinetic energy, the total kinetic energy. It becomes 1/2, and the omega is in every term, and it's the same, so it's a constant. It can come out, and that's omega, and then this becomes sum of m sub i's, r sub i's squared. Now this definitely becomes the moment of inertia. Okay, so all right, so now this is looking really great. Oh, one more thing, I made a mistake here. You probably noticed it. This is squared, and so I needed to put this as squared here, and then when I take it through, it's still squared. Okay, so that's important. Almost made a mistake there. Okay, so our final expression here is that the kinetic energy, the total kinetic energy for this whole thing rotating is going to be 1/2, and of course this is I omega, oops, Let me write that as a proper omega instead of a omega squared. Of course, this looks very similar to 1/2 mv squared, just like what we had done with our analogies. But in this case, I actually used this from a rotating wheel. So, and the equations all check out. So it checks out, all right? So let's do a rotational version of work next. So let's look at the version of rotational work. Remember that the traditional version of work for linear things was that we're taking the part of the force and the distance that are parallel to each other and multiplying those two. Okay, so in this case, we have a wheel, and this is just a simple situation. It's not representative of every possible scenario, but this is just an example to kind of get the equation for this particular example, and that motivates it for the rest of them. So this isn't a rigorous definition or derivation, that is. The work done for this force acting on this wheel here that's free to rotate about the axis in the center is going to be when, if this force acts on some point on the wheel, and then the wheel rotates through some distance delta s. So this wheel rotates like that. Remember that to find the work, we need to multiply the part of the force that's parallel to this displacement. This displacement goes this way, and so we need the part of the force that's parallel to that. But that part of the force is perpendicular to our r vector from the center of the axis here. So I'm going to call this F perpendicular. So this F perpendicular, I'm going to take that and multiply that part of the force times delta S here. And remember that I'm calling this F perpendicular because it's perpendicular to R, my vector R, okay? So those are the parts of the force and the displacement that are in the same direction. And so when this thing moves through some displacement delta S here, this thing is going to rotate. And so here's the radius here. It's going to rotate through some angle. I'm going to call that angle delta theta. Now recall that the angle delta theta, there's a relationship between R and S, and that is that delta S is equal to R delta theta. That's the basic arc length formula that we talked about, even going back to the beginning of the semester. Just I wanted you to memorize this. It's such a useful equation that we use it over and over again here. I'm going to substitute that in up here. So the work done is just F perpendicular, and again, that's the part of the force that's perpendicular to R, times, that's going to be R delta theta. Okay, and I'm just substituting that in. Well, this part here, F perpendicular times R, well, that is the torque, right? That's the part of the force that's perpendicular to the R vector that goes from the axis of rotation to where the force acts. That is torque. So this work is going to be the torque times delta theta. Okay. Now, if I shrink these deltas into really tiny, infinitesimally small angles, then that's going to shrink this. This is going to become differentials. That's what these differentials represent, is really, really tiny amounts of that quantity. So a tiny d theta is going to be a tiny, tiny angle. And this delta S is going to become a tiny displacement. And so the if I want to do the version of this where the torque might change, then I'm going to do an integral of torque d theta here, okay? Well, if you recall, that looks very similar to the rotational or the linear version here, and that would be the work is equal to the integral of F ds, okay? Where F becomes the torque, and because that's the rotational version of force, and the displacement here becomes the angle because the angle is the rotational version of position, okay? So hopefully this motivates the idea of rotational work. There's one more thing I want to tell you here, and that is that we had this idea that the change in kinetic energy is due to the net work done, and that is no different. Because the kinetic energy that we derived for rotations is still in joules, and the work done we derived is still work. It's not a different thing. It's still work, and it's going to still be in joules. This equation will be the same. But in this case, we need to think about the rotational and the translational. So this delta KE becomes 1/2 mv final, plus I have to consider the rotational kinetic energy, 1/2 1/2 I omega final. That's the final kinetic energy. This is the KE final. And then I have to subtract from that the initial kinetic energy. And that's going to be 1/2 mv initial squared. Excuse me, I need to square these. Sorry about that. Plus the 1/2 the rotational kinetic energy. That's 1/2 I omega initial squared. Okay, so that's the change in kinetic energy. And when I do this term, this is the center of mass. This is the center of mass velocity here. Okay. And then this rotational term is the angular velocity that's rotating around that center of mass. Okay, so we're combining the center of mass rotation. This is translational plus rotational. Okay, that's what we're doing here. And we do the same for the work, right? So the work done is going to be equal to the translational work plus the rotational work. So okay, so you have to add those up in the same way. Now, we're not going to do a whole lot of things where you have to consider both of these, but if you did, that's how you would add them. You just add them because they're still the regular work and the regular kinetic energy. They don't have different units, and they're not a different thing. Okay. All right. Hopefully this helped. I would encourage you strongly to check out the examples. Those are going to be a lot better and more informative and give you a really good idea on how to use these. All right. See you later.